Welcome back, class. So, with this lecture, we are going to start beginning our look at Chapter 3. So, in this chapter, we're going to look at molecules and compounds. So, within this chapter, we're going to look at the different types of compounds. We're going to learn how to name some of these different types of compounds. We're going to look at how we can apply some of the ideas we learned before, such as the mole concept, to quantifying compounds, and then look at some other ways that we might be able to analyze compounds or come up with the formula of compounds based on experimental data. So let's first of all just go into looking at what makes up a compound and how are these compounds held together. So if we remind ourselves of the definition that we've talked about previously of a compound, it's two or more different elements combined in fixed, definite proportions, right? So we looked at this back in Chapter 2 when we talked about the law of definite proportions and multiple proportions, etc. And we came up with this definition. So we're going to be looking at a compound. Now remember also the smallest unit is a molecule, right? So we call the smallest unit of a compound a molecule. Now, it's because these compounds contain two or more different elements that are combined, right? Those elements must be held together somehow, right? So the atoms that are in our compounds must be held together somehow, and they're held together by chemical bonds, right? And all chemical bonds form due to what we call electrostatic attractions. And what this simply means is attraction of opposite charges. So all types of bonds that we're going to talk about ultimately come down to being formed by attraction of opposite charges. So what are the different types? And what are some of their differences? Well, we're going to talk about two major types. The first one is what we call ionic bonds. And some basic ideas of ionic bonds is that the vast majority of them are made between a metal and a non-metal. So it's a bond between a metal and a non-metal. That bond involves a transfer of electrons, typically from the metal to the non-metal. So we have a bond between a metal and non-metal that involves transfer of electrons. We find ionic bonds in ionic compounds. So this is the first type. Second type is called a covalent bond. And a covalent bond is formed between two non-metals. So no metals are involved. It involves, instead of the transfer, the sharing of electrons. Now, more specifically, all of the bonds that we're going to talk about involve the sharing of two electrons. They're going to be what we call 2-electron bonds. And these are formed by the attraction between protons and electrons. So again, we have the positive charge of the protons interacting with negative charge of these shared electrons. And these are present in molecular compounds, which are sometimes referred to as covalent compounds, but more commonly we refer to molecular compounds. So we have ionic compounds which contain ionic bonds, and molecular compounds which contain these covalent bonds. Now, if we look a little more closely at ionic compounds in the next slide, but just to touch on molecular compounds, and to talk a little bit more about this attraction, right? The way we visualize a covalent bond is if we were to take, say, the nucleus of one atom, right, and we were to then have our shared electrons, and it's, again, typically we're going to talk about 2-electron bonds, so we've got the sharing of 2 electrons and the nucleus or the protons of the other atom involved in our bond. So it's the mutual attraction between the protons in the nucleus of our 2 atoms that are involved in the bond with these shared negatively charged electrons. That's where we get our covalent bond. Now we're going to touch on this in more detail starting in chapter 10. So let's focus a minute on ionic bonds. So if we look at the formation of a sample ionic bond, so let's say we're combining sodium, right, and chlorine. And we're ultimately making sodium chloride, salt, right? So we have sodium metal, right? Neutral, right? A metal. We have chlorine, right? We'll talk about more about this later, but chlorine exists as Cl2 molecules, but we have a non-metal chlorine. Now, remember what we talked about last chapter when we talked about the formation of ions, right? We said that metals like to form positive ions. So in other words, they like to lose electrons, and non-metals like to form negative ions. In other words, they like to gain electrons. So that's why we talk about the transfer of the electron from the metal from our metal sodium to our non-metal chlorine, which gives a sodium positive ion, which now has one less electron, and a chloride negative ion, which has one more electron than the neutral atom. So now we have this positive and negative ions that are attracted to each other, and they come together to form our sodium chloride, right? Now, one important thing that we're going to note here about ionic compounds, right? So we're forming an ionic compound here is that ionic compounds exist in a lattice. So a lattice is simply a three-dimensional structure with alternating positive and negative ions. And this crystal lattice is neutral, right? So these compounds are neutral, right? So you have to have the same amount of positive charge as negative charge. And that's when we write out the formula of an ionic compound, that's what we're writing, right? We're writing the simplest neutral formula of the ions. So since sodium is a positive 1 and chloride is a minus 1, we put 1 and 1 together, and that gives us a neutral formula. Right? This, and we'll see this term later, this is what we call a formula unit. So when we talk about ionic compounds, there are no such thing as molecules in an ionic compound because everything is in these large lattice structures, but we have this simple neutral unit which we call a formula unit. So it's like the analogous to a molecule in a molecular compound that we'll talk about later. So a little bit more in detail about ionic compounds at this point in time, and again, we'll talk more in detail about molecular compounds beyond the naming, etc., in some later chapters, starting around chapter 10. So at this point, let's talk about ways that we can show these compounds, right? So we have these ionic compounds and these molecular compounds. How do we write them out? Well, we're going to show them by using what we call chemical formulas. And there are a couple different types of chemical formulas that we want to define here. The first one is the empirical formula. And so the empirical formula is shows the relative number of atoms of each element. So it's what we typically would call the simplest ratio. Of the elements. Now, where we most commonly see this is in our ionic compounds, right? When we write out the formula of an ionic compound, like sodium chloride, what we're showing here is the empirical formula. So these formula units that we talk about are the simplest ratio of the elements, right? Neutral ratio of the elements. Okay, so we got empirical formula. The second type is we have the molecular formula. This shows the actual number of atoms of each element. So whereas the empirical shows the simplest, the molecular formula shows the actual number of atoms of each element. And we're going to say in a molecule. Of the compound. So, of course, where we tend to see these are in molecular compounds. This is how we most often show molecular compounds. So if we look over here, we can see some examples, right? So the molecular formula of what this is methane. Yes, CH4. So every molecule of this molecular compound contains 1 carbon and 4 hydrogens. Now, some other ways that we can show these formulas, right? So these are going to be alternative ways to show a molecular formula. We can show what's called a structural formula. And what a structural formula does is add bonding info. So it shows us which atoms are bonded to which other atoms. So in here I can see that the carbon is bonded to each of the 4 hydrogens. So it shows a general structural layout of how things are connected. Now, we can also get into more 3-dimensional structures, where we have what's called a ball and stick model, which shows a basic 3-dimensional layout. So we move from structural to ball and stick, we go from a 2-dimensional representation to a more realistic 3-dimensional representation. And there's various kinds of this. Right? We can also show this as what we call a space filling. This is going to be, the most realistic of sort of how the molecule would look. And this is often used in book art, and you'll see, like when you show in the book, when they show all these molecules, oftentimes they'll show them in a space filling representation, because it gives us sort of the best visual of what the molecule actually looks like. Now, we'll utilize especially ball and stick and structural formulas, again, once we get into chapter 10 and 11 and we start diving more into molecular compounds and their structure. Let's just do a little bit of practice to emphasize this idea of empirical versus molecular. So if we're given the formula C6H12O6, right? So this would be a molecular formula. And if we wanted to write the empirical formula, we need the simplest ratio of the atoms. Now, we have to be a little bit careful here, because it's probably really easy to just simply say, 6, 12, 6. I can simplify this. C3H6O3, right? Divide by 2, right? Now, but if we look closely at this, this is not the simplest, right? Because we can still reduce this further, right? So what we want to do is we want to find the biggest factor that we can divide each of these by. So it turns out we can divide all of these by 6. And what we really end up with is CH2O, right, as my empirical formula, not that. So again, we have the simplest, right, there's a 1 to 2 to 1 ratio of carbon, hydrogen, and oxygen, and we have the molecular formula, what each molecule of that compound actually contains. Look at the second example, sucrose, right? And what we should determine here is that this is already the empirical formula. So because we can't reduce this is the simplest ratio. There's no factor that we can reduce these by. And so in a lot of cases, right, the molecular formula equals the empirical formula. And we look at our last example here. Turns out we can divide each of these by 2 is the biggest factor, right? And so if we do that, we end up with C4H5O2, N2O as my empirical formula. So just a little bit of practice on the difference between molecular formula and empirical formula.